Welcome back. So today is our third lecture on randomized algorithms, and we're going to talk about Chernoff bounds. So Chernoff bounds are not a type of randomized algorithm. Instead, it's a mathematical technique that can be used to analyze the performance of randomized algorithms. And they're very widely used in all aspects of randomized algorithms. So today, we'll look at what the Chernoff bounds are, and we'll give some examples of how to use them. Okay, so to start out with, Chernoff bounds deal with the expectation of a random variable. Okay, so let's just recall that for a random variable x, the expected value e of x is the value that what you expect to get for x, meaning that if you take many samples of x, according to the probability distribution for x, then if you look at the average of all of those values, then that average is going to come out to e of x. Okay, but because it's an expectation, then of course you don't expect every sample of x to produce exactly this value, right? On the other hand, because it's an expectation, you also don't expect the values of x to be very different from x, from e of x, right? At least you don't expect many samples of x to be very different from e of x. Okay, so then we can ask the question, how different do we expect x to be from its expectation? So as an example, suppose you take a coin and you flip it 100 times. Okay, so it's a fair coin, so you expect to get 50 heads. Right, so the random variable is the number of heads that you get after 100 coin flips. So that can be anywhere between 0 to 100. And we expect to get 50 heads. So now you can ask, what is the probability that the actual value of the random variable, the actual number of heads that we get, is actually different from the expectation? Okay, so what's the probability you get 60 heads? Okay, what about 80 heads? What about getting 100 heads? Okay, so we want to figure out these probabilities. And now, why is this related to randomized algorithms? Well, it's because in a randomized algorithm, the algorithm is going to make a bunch of random decisions. And so therefore, the output or the behavior of the algorithm is itself a random variable. Okay, so for example, the running time of the algorithm. So if you have a Las Vegas algorithm, right, then we know that the running time is not necessarily a fixed value. It can actually deviate. Okay, so the actual running time of a Las Vegas algorithm is a random variable. Okay, and so we saw some examples, for example, with quicksort, right? We saw that it usually is not very difficult to bound the expected running time of an algorithm. For example, you can use something like linearity of expectations, and you can break the algorithm into a bunch of small parts, and you can bound the expectation of each part. And then when you add those up, you get the expected running time for the entire algorithm. Okay, so oftentimes we can actually get a good bound on the expected, let's say, running time of an algorithm. But now the question is, how likely is it that we deviate away from this expectation? So for example, when you run quicksort, we know the expected running time is going to be n log n. Okay, well, what is the probability that you actually deviate significantly from this? So for example, what's the probability you run for n times log squared n amount of time instead of n log n, right? Or what about the probability of actually running for n squared amount of time, right? So we know that it's possible that the randomized quicksort algorithm runs for n squared amount of time, but we would like to bound the probability of this happening. And the Chernoff bounds actually allow us to do this, okay? They tell us the probability that a random variable is very different from its expectation, right? And just to give you a preview of the bounds, so of course we'll have more precise statements later, but basically the probability that a random variable differs from its expectation is very low, okay? It's in fact exponentially low. And the larger the expectation is, the smaller the probability of this deviation. Okay. However, we're going to need some assumptions on this random variable, as we'll see later. Okay. So that's kind of a preview of the Chernoff bounds. So now, sorry, 1 second. Okay. So now, before we actually get to the Chernoff bounds, let's first talk about some simpler inequalities, simpler probabilistic bounds. Okay. And then we're going to use these to build up to the Chernoff bounds. And so, in fact, some of these bounds are used in the proof of the Chernoff bounds. Okay, so the first bound that we're going to start with is this thing called Markov's inequality. And what it says is that suppose we have a positive random variable x. Okay, then what's the probability x is larger than a certain value a? Okay, so we can take any positive value a, right? And we're asking what's the probability x is larger than a? And the Markov inequality says that this is at most the expected value of x divided by a. Okay, so as an example of this, suppose we have that x is a random variable equal to the number of heads after we flip a coin 100 times. Okay, so again, we get a number between 0 to 100. Right? So now, yeah, so this is a positive random variable. X is positive, right? Or non-negative at least. So now, what's the probability that x is larger than 60? Right? Well, according to Markov's inequality, this is going to be less than the expected value for x, which is 50, right? Because if you have a fair coin and you flip it 100 times, then you expect 50 heads, right? So this is going to be less than 50 divided by a here, which is 60. Okay, so it's at most 5, 6. Okay. And you can kind of see that this is intuitively true, right? Because, for example, suppose that, so here it's saying that, the probability is less than 5, 6. Suppose this was not true, okay? So suppose it was actually more than 5, 6, okay? Suppose the probability that x is larger than, x is at least 60, suppose that's actually equal to like 90%, okay? Is that possible at all, okay? Yeah. So suppose, this was actually equal to like 90%, okay? Now, this is going to be impossible by Markov's inequality, right? But let's just see intuitively why this is impossible. Well, the reason is that if the probability x is larger than 60 is 90%, okay? Then if you take a sample of x, right, then 90% of the time, you get a value which is at least 60. Right, you might get a value even larger than 60, like 70 or 100. Okay, but it's going to be at least 60. Okay, so therefore the average value for x. Okay, so then if we have this probability is equal to 90, then that would imply the average value for x, right, which is equal to the oops, let's write this a bit nicer, which is equal to the expectation of x, right. So this would be at least 0.9 times 60, because we have a 90% chance of getting something which is at least 60. Okay, so the average value is going to be at least this, and then this, of course, is equal to 54. Okay, so this would mean that the expected value of x is actually 54 instead of 50. Okay, and that's a contradiction. Okay, so that's why this probability here cannot be very large, because if it's very large, then when you multiply it by this, by this value over here, you're going to get something larger than the actual expected value. Okay, so that's just an example to convince you that it's true. So we can actually formalize this a bit, and then convert this to a proof. Okay, so we're going to prove the Markov inequality. And the proof is by contradiction. Okay, so the proof, so now suppose we have a value a, and the probability that x is at least a is larger than the expectation of x divided by a. Okay, so this is not true, but let's see why. Okay, then by the definition of expectation, okay, so expectation is that we take all of the values of this random variable, right, and then multiply each by the probability of getting that value. That's the definition of expectation, right? And now, because all of these values for x are positive, right? So remember that we require x to be positive, okay? Then all of these terms over here are also positive, okay? So therefore, if you take out some of these terms, right, your sum can only get smaller. So therefore, if we take out all of the terms for x less than a, okay, so we only keep the terms where x is at least a here, okay, then we have that, we have this inequality here. Okay, and now because all of these values for x are at least a, right, then we have that, this sum over here is going to be at least equal to this value. Because all of these x's are at least a, so we can actually pull all this x out and we can replace it with an a, right? And we have this inequality. Okay, so yeah, so now we have that a times the probability x is at least a is larger than, now we can, by assumption we have that the probability x is at least a is larger than the expectation of x divided by a. So then we can do the substitution over here. Right? And then finally, we have a times e of x divided by a, which is e of x. Okay, and now we have a contradiction because we have that the expected value is actually larger than the expected value. Okay, so that's the proof of Markov's inequality. Okay, so so Markov's inequality does give us a bound on what is the probability that you have a random variable which is very, very large. Okay, and it says that well, compared to its expectation, there's a bound on this probability. Okay, so the problem with Markov's inequality is that the bounds it gives are usually very weak. So, for example, if we use this example with the number of coin flips again, okay, so if we use that over here, right, if we use the previous example, then if we set a to be 101, okay, so we're asking what is the probability that you flip the coin 100 times, and then you get at least 101 heads. Okay, well, if we simply use Markov's inequality, then we just take the expected value and then divide by a, and that's going to come out to something like 49%. Okay, so it's saying that, well, you've only got at most a 49% chance of getting more than 101 heads. Okay, but of course we know that we're not going to get 101 heads, right? Because we only flip 100 times. So we have a 0% probability of getting 101 heads. Okay, whereas Markov's inequality only says that, well, you have no more than 49% probability of that happening. Okay, so you see that Markov's inequality doesn't actually give us a very tight bound. Okay, so that's the main drawback to Markov's inequality, is that it's not tight. However, Markov's inequality also has some advantages. One of which is that it's very general, because Markov's inequality doesn't assume anything special about these random variables. Right? The only property that we need is that x is a positive random variable or non-negative random variable. Okay, so we're going to see that when we try to use some other inequalities, we need to make some special assumptions about x. Okay, so those are those other inequalities, even though they might give tighter bounds than Markov's inequality, they apply in fewer circumstances. Okay, so now because Markov's inequality is so general, then we can actually use it in certain ways to prove stronger statements. Okay, so we're going to see, so in fact, the Chernoff bound is proven, one of the key steps in the Chernoff bound is to use the Markov inequality. Okay, now before we get to Chernoff bounds, let's first see another application of Markov's inequality. And so this is going to produce the Chebyshev inequality. And so this is also quite a useful inequality in practice. Okay, so the Chebyshev inequality says that suppose you have a random variable x, and then any a value larger than 0. Okay, so now we're going to look at what is the probability that a sample of x differs from its expected value by at least a in absolute value. Okay, so basically, what's the probability x is at least a larger than the expected value, or at least a less than the expected value? Okay, and this probability by this inequality is at most the variance of x divided by a squared. Okay, so yeah, so let's first prove this inequality. So so by definition, the variance of x, sorry, the variance of x is equal to the expected value of the deviation of x from its expectation squared. Okay, so you take x, you subtract the expectation, right, and then you square it. Okay, so that's some other random variable. And then if you look at the expectation of that random variable, that's the definition of the variance of x. Okay, so then so now you know this value here is what we're trying to compute for Chebyshev's inequality. Okay, and so if you just square both sides, right, then you get that this is you know, this probability is equal to the probability of this thing happening. Okay, x minus e of x squared is at least a squared. Okay, and now we can just use Markov's inequality. Okay, so Markov's inequality says that well, this here is a random variable, right? So you can call this y, right? So Markov's inequality says that the probability of this thing happening is at most the expectation of y, right, divided by this value here, which is now a squared. Okay, but what is the expectation of y? Well, the expectation of y is, as you can see over here, right, it's just equal to the variance of x. Okay, so therefore, just by Markov's inequality, we get that this thing is less than the variance of x squared, divided by a squared. Okay, so so now we can apply Chebyshev's inequality. So let's use it on the previous example again with flipping coins. Okay, so x is the number of heads in 100 coin flips, and now in order to use Chebyshev's inequality, we have to be able to compute the variance of x. So the variance of x. So if you just take one coin flip, okay, so you have a 1/2 probability of getting heads, and so the variance of that random variable for one coin flip is just 1/4. And here you're flipping the coin 100 times, and so the variance is going to be 100 times divided by 4. Okay, so then using Chebyshev's inequality, you have that the probability that x differs from its expectation, let's say by 10 over here. Okay, so this is going to be at most the variance, right, divided by 10 squared. So that's at most 1/4. Okay, so this means that now here we're taking x minus 50, the absolute value of that is at least 10. So this means that you're going to get, we're asking what's the probability you get at least 60 heads or at most 40 heads. Okay, yeah, so this probability here is actually the sum of two other probabilities, which are disjoint from each other. And also, those two probabilities are equal to each other, right? The probability you get more than 60 heads is equal to the probability you get less than 40 heads, right? Because heads and tails have equal probability. Okay, so therefore the probability you get more than 60 heads is just going to be 1/2 of this. Okay, so it's going to be at most 1/8. Okay, so now we can actually compare this with what we got from Markov's inequality, which was now let me erase some of this stuff. This is too messy over here. So Markov's inequality, if you just apply directly, right, we saw that the probability you get at least 60 heads is no more than 5/6. Okay, and then here Chebyshev's inequality gives us a much tighter bound because it's saying that the probability is at most 1/8. Okay, so yeah, so we see that we're getting the stronger bounds now, and so in fact we want to have even stronger bounds. Okay, so the Chernoff bounds are going to be even stronger than the Chebyshev bounds. Okay, so in order to talk about the Chernoff bounds, so the Chernoff bounds deal with expectation of random variables, but they're a special type of random variable. Okay, so in fact, the type of random variable that Chernoff bounds applies to is where the random variable is a sum of other random variables, and these other random variables have to be independent from each other. Okay, so we're going to consider a special type of random variable. Let's call it x. Okay, so x is going to be the sum of n independent random variables, okay, for some number n. Okay, so let's say you have a bunch of random variables and they're independent from each other, and then if you add them all together, then that's x. Okay, and now we're going to look at how likely x is to deviate from its expectation. Okay, so so the expectation of x, in fact, is equal to the, so by linearity of expectations again, the expectation of x is equal to the sum of the expectations of these n independent random variables, right? And so the question is, how likely is x to deviate from that expectation? And the intuition is that as you increase the number of random variables that make up x, okay, then x should really start to approach e of x, okay, at least in relative terms, in like sort of percentage terms, right? Like how many percent deviation is there between x and e of x? Okay, that percentage difference should really get smaller as n gets larger. Okay, so as an example of this, suppose x is the sum of, let's say, suppose x is the number of heads you get, okay, after you flip n coins, a coin n times. Okay, so all the flips are independent, right? Now, if n is 10, right, so you flip the coin 10 times, right, so you expect to get 5 heads, but if you ask for the probability you get like 6 heads, right, well, you've got actually a decent probability of getting 6 heads or 6 or more heads. Okay, that's a pretty large probability actually. Okay, and that's because you're only adding up 10 independent random variables. So n is not very large here. But if you make n much larger, right? So if you make n like 1,000, okay, and now you still ask, well, what is the probability I get a 10% deviation from my mean, right? So previously, if I flip the coin 5 times, then if I get a 10% deviation, that means I get 6 or more heads. Okay, but if I flip the coin 1,000 times, then if I want to get a 10% deviation, then I would have to get 600 or more heads. Okay. And there, you expect to have a very low probability of getting 600 or more heads if you flip the coin 1,000 times, right? In fact, if you flip it 1,000 times and you get like 600 heads, you would probably suspect that you do not have a fair coin, right? Because a fair coin, you expect the deviation from the mean, which is 500, you expect that to be much, much smaller. Okay, so that's basically the phenomenon that Chernoff bounds capture. Okay, it's to say that this convergence between x to its expectation in these percentage terms, in relative terms, okay, is going to be very fast. It's going to be exponentially fast as you increase the number of these random variables. Okay, yeah. So here I'm just sort of numerically doing out this example I was saying. Okay, so here if you want to get like 10% deviation from your mean, right? Your mean is 50% heads. If you want to get 10% deviation, right? Then for small n, okay, you've actually got a large probability of this happening. Okay, in fact, I made a plot of this, the probability that you get at least 10% deviation as you increase the number of coin flips from like 0 up to 100 over here. Okay, if you flip it 20 times, if you flip the coin 20 times, right, the probability you get at least 60 heads is now, you see it's smaller, right? So it's decreasing. And in fact, if you make n 100, then you already have that, you have no more than like, 3% probability of getting 60% heads. Okay, so this probability here is like decreasing very fast, okay, which you can see from this plot over here. Okay, so that's the basic motivation behind Chernoff bounds. Okay, so now let's actually state these bounds. So there are actually many variations of Chernoff bounds. Yeah, so they apply in slightly different circumstances, and they have somewhat different statements. In fact, when you first look at these, it looks like these different Chernoff bounds are quite different from each other. Okay, but usually it's just some sort of algebraic manipulation to get from one bound to another. Okay, so I'm going to present to you several versions of the Chernoff bound because different versions are easier to use in different circumstances. Okay, but essentially all of these bounds are saying the same thing. Okay, essentially all of them are bounding the the probability that you get some sort of percentage difference, a percentage deviation from your mean. And this is going to be exponentially small. Okay, so more precisely, suppose you have n independent random variables here, x1 up to xn. Okay, and each of them can have a different expectation. So let's say that p of I is the expected value of x of I. Okay, so next we're going to take the sum of all of these random variables, and we're going to call that x. Okay, and the expected value of x is just the sum of the individual expectations. And so let's call that value mu. Okay, so now we have a Chernoff bound, and it involves this parameter delta here. Okay, so we're going to look at delta in different ranges. So for example, for delta in the range from larger than 0 and then at most 1, okay, then the probability that x is at least 1 plus delta times its expectation, right, is going to be at most this quantity here. Okay, it's going to be e to the negative mu times delta squared divided by 3. Okay, so so as an example of this, suppose delta is let's say 0.1. Right? Then what this first part of the bound is saying is that what's the probability x is at least 10% larger than its expected value. Okay, and here the probability is going to be, so delta here is now just a constant, right? So it's 0.1. So you have 0.1 squared divided by 3. That's 1 over 300. Let's just call that value. Okay, so that's going to be 300 here, right? All right, and this is saying that so the probability is going to be at most e to the negative mu divided by 300. So now you see that as mu gets larger, right, this probability actually decreases, right? In fact, it decreases exponentially fast. So in fact, if you, let's say for simplicity, all of these, let's consider a simple case where all of these random variables have the same expectation. Okay, so it's just, let's say p. Okay, so then as you increase n, right, then this expected value here is just going to be n times p. Okay, so the more independent random variables you have, the bigger mu is, and what this is saying is that as this mu increases, right, then the probability you get a 10% deviation is going to decrease exponentially fast. Okay, so that's the first case for the Chernoff bound. Okay, and we'll do more examples later, but that's the first case. The next case is where delta is larger than 1. Okay, so here we're still looking at the same probability. Okay, so what's the probability you get at least delta fraction larger than your expected value? Okay, now the bound here is going to be a little bit different. Okay, so but it's only different in this sort of constant term in the delta. Okay, it's still going to be exponentially decreasing in the mean. All right, yeah. And so that's so these are the probabilities that x is larger than its expected value. Okay, but we also have the other side where we don't expect x to be much less than its expected value either. Okay, so in that case, we have the third case for the Chernoff bound, which is that for mu between 0 to 1, right? What's the probability that x is much less, right? Much less than its expected value. And again, this is going to be something which is exponentially decreasing in the mean, and we have another constant term over here. Okay, so if you just compare all three versions of these Chernoff bounds, well, all of them are bounding the probability that x is either much larger than its mean or much less than its mean. Okay, and all of them are exponential, both in the expected value of x, and also in these terms involving delta. Okay, the only difference is that these delta terms have slightly different forms. Okay, so that's the statement of the first variation of the Chernoff bound, and then we have different variations which I'll show you later. Okay, but first let's see why Chernoff bounds are useful in terms of randomized algorithms. Okay, so in fact, it turns out that Chernoff bounds are used all over the place when you analyze randomized algorithms. Okay, and so this is because usually we saw different ways of analyzing the expected, let's say, running time of a randomized algorithm, right? Or maybe the expected probability that it outputs incorrect values. Okay, so if you have a Monte Carlo algorithm, then it can actually the algorithm can produce incorrect outputs. Okay, so we can oftentimes analyze the expectation of the incorrectness probability. Okay, but we don't want just an expected value, right? Because we want to say that, for example, quicksort. We don't want to just say that in expectation it's going to run in n log n time. We actually want much tighter bounds. We want to say something like, there's at most a 1% probability that it runs in more than, let's say, 2 times n log n time. Okay, we would like to have statements of that sort. And Chernoff bounds are are a tool that often enable us to make very strong statements of those forms. Okay, and the reason that we can use Chernoff bounds when you analyze randomized algorithms is that oftentimes the algorithms are doing things in stages, and the stages are independent from each other. And so you can compute the expected cost of each stage. Okay, that's usually easy to do. And because the stages are independent from each other, right? So this is often the case. Of course, it's not always the case, right? But in many algorithms, you have these independent stages, and if you can compute the expected cost of each stage, then the total cost of the algorithm is just the sum of the cost of all the stages. Okay. And then now, because the Chernoff bound puts bounds on the probability of the sum of random variables, right? Then it's going to give us a bound on the probability on the cost of all those stages, right? Because that's just the sum of the individual stages. So as an example of this, for example, when we considered quicksort, right, or randomized quicksort. So there we had a bunch of stages which were these divide and conquer steps, where you pick the pivot and then you split your array into 2 parts. Okay, and then so what we wanted for those pivots was that the pivots are close to the middle. Okay, they don't have to be exactly the middle element, but you don't want them to be too different from the middle element. Okay, so in fact we saw that it was enough, for example, just for the pivots to be like in the middle half of all of the elements. Okay, so between the 25th percentile and the 75th percentile, right? As long as we pick the pivot somewhere in there, then we could have this recurrence, which eventually solves to n log n. Okay, and now because you just need the pivot to be within the middle half of all of those values, right? Then what is the probability of that happening if you pick a random pivot? Well, that's just going to be 1/2. Okay, right? Because you just need the pivot to be within that middle half. Okay, so therefore we have that we expect each stage. So each stage is where you pick the pivot and divide the array. We expect each stage to have low cost. Okay, and then the overall cost is just the sum of all the stages. Okay, and so then you can use the Chernoff bound to show that not only do we have n log n behavior for quicksort in expectation, we also have that with very high probability, the actual running time is very close to n log n. Okay, so with very, very low probability, for example, are we going to get something like n squared running time? Okay. All right. Okay, and then here I'm just saying that there are different variants of these Chernoff bounds. Okay, so and the variant that you use depends on your situation, because these variations are basically taking like this basic Chernoff bound and then sort of specializing them to certain situations to make the bound a bit easier to use. Okay, so I'll give you 2 of these variants. So the first variation is this theorem 2 over here. Okay, so again, we're going to have these, we're going to define all the variables the same as before. Okay, so we have these n random variables which are independent from each other. And then we have this x, which is the sum of all of these random variables. Okay, and now we have that for any delta larger than 0, right? What's the probability that x is at least 1 plus delta times its expected value? Okay, well, that's going to be no more than this term. Okay, so this is some complicated term, but you see that all the terms involving delta, so if you think of delta as a constant, then all the terms involving delta are over here, right? And so this is some sort of constant. And then, yeah, and then usually it's going to be less than 1, right? If it's more than 1, it's not useful. Yeah, usually this is going to be less than 1, so you can pick delta so that this is going to be less than 1 here, right? And then you see that this probability is going to be exponentially decreasing in the mean. Okay, so as we saw before. Okay, so the next variation is going to be that, so now we're not going to have arbitrary random variables for x1 and xn. So now these are just going to be Boolean valued variables. Okay, so they're either -1 or +1. Okay, so that's not Boolean, but anyways, so they're -1 or +1. Okay, and they're independent from each other, right? So we always need that the things that we're summing are independent in order to apply Chernoff bound. Okay, so yeah, I forgot to mention, so if you want to compare Chernoff bounds with the Markov inequality, for example, okay, so remember that Markov was very general and it doesn't assume anything about the random variable except that it's positive, right? But Chernoff bounds, you need to have a very special form for this random variable that you're analyzing, right? It needs to be, first of all, the sum of other random variables, and those other ones need to be independent. Okay, so that's a pretty strong assumption of independence. Okay, yeah, so that's why it's not possible to use Chernoff bounds in all circumstances, or at least you have to transform your problem so that it's that you achieve enough independence between these variables that you're summing in order to apply some sort of Chernoff or related bound. Okay. But sometimes you just get that these variables are independent for free. Okay, so in that case, you can just directly apply the Chernoff bound. All right, so for for this case where we have independent variables which are either -1 or +1. Okay, then let's also assume that the probability that each variable is oh, sorry, this should be an I over here. Okay, let's assume that the probability each variable is going to be 1 or -1. It's both half. Okay, so so this is kind of like a coin flip, right? You either get a 1 or -1 with equal probability. Okay, and now let's let x be the sum of all of these xi's. Okay, so now first of all, the expected value of big X, right? So this is going to be 0 because each of these individual xi's has expectation 0. Right, because it's going to be 1 and -1 with both with probability 1/2. Okay, so therefore we expect x to be 0. Okay, so now we can ask what's the probability that x is actually not 0? Okay, so what's the probability it's actually at least delta? This is going to be equal to the probability that x is less than delta. Oh, sorry, less than negative delta. Okay. And this is because you know, x is 1 and -1 with the same probability. Okay, and now this is going to be exponentially decreasing in delta. Okay, but divided by 2n. Okay, so that's the third form of the Markov inequality. Sorry, of the Chernoff bound. Yeah, I'm looking at something else here. All right, so now before we actually start using the Chernoff bound to do certain things, let's give a proof of the Chernoff bound. Okay, so so we have a bunch of these different variations. So I'm not going to prove all of them. Instead, I'm just going to focus on theorem 2 over here. Okay, so this in some sense is like the most general form of the Chernoff bound, because for example, using this theorem 2 here, right, then just by doing some simple algebra, you can actually derive the different forms in theorem 1, okay, and theorem 3. Okay, so in fact, this is like sort of the most fundamental form of the Chernoff bound. Okay, now I'm gonna slightly simplify this theorem 2 over here. Okay, so theorem 2 here, the different random variables can have different expectations. Okay, and in fact, they're a general random variable, so they can take on any value. Okay, so instead, I'm gonna simplify these so that the random variables that we consider are going to be Bernoulli random variables. Okay, meaning that they're either gonna be let's see, so they're gonna be 0 or 1, right? And then so they're gonna be either 0 or 1, and it's gonna have a probability P of being equal to 1. Okay, and furthermore, we're gonna assume that here in the simplified proof, all of these x's are the same. Okay, so they all have the same probability P of being equal to 1. Whereas in this theorem 2 over here, we allow all of these x's to be arbitrary random variables, so they can have arbitrary values, and they can be different from each other. Okay, so our proof is going to be simpler in that we assume all these random variables are the same as each other, and they can only be either 0 or 1. Okay, but nevertheless, this proof is going to basically capture all of the key ideas which are used in the more general proof. Okay, so yeah, all right. So let's do the simplified proof, and this proof I directly copied all of these all of this stuff from Wikipedia. Okay, so this is the Wikipedia article on the Chernoff bound, and it gives a very nice and concise proof of this. Okay, so instead of rewriting everything that Wikipedia already has, right, I just did like a screen capture here. Okay, so you can get all the details from Wikipedia, and they have some. In fact, they have some other examples and some more proofs over there. Okay, all right, but let's go through this just to see what the main ideas for the proof are. So yeah, so the first step to this proof is actually to apply Markov's inequality. Okay, so Chernoff bounds is a consequence of or it's derived using the Markov inequality. Okay, so so the thing we want to answer for the Chernoff bound is what's the probability of a random variable x, okay, where x here is the sum of a bunch of other random variables, independent ones, right? What's the probability this is at least a? Okay, so now the first thing is we're just going to exponentiate both sides. Okay, and we're gonna multiply by some value t also. Okay, so so t here can be any value larger than 0. All right, so yeah, I'm not gonna necessarily explain the motivation for this, but let's just do this. So we're gonna do so this probability here is equal to we're gonna multiply both sides by t and then exponentiate. So therefore, these two probabilities are equal to each other. Okay. And now by Markov's inequality, this probability over here is just equal to the expected value of this. So this here is a random variable. So it's equal to the expectation of that random variable divided by the right-hand side, which is e to the t times a. Okay. And now, because this x here is a sum of, so x here is a sum of a bunch of other, random variables, right? And then all of these things are being multiplied by t. And since we're taking the exponential of this x here, okay, then if we then all of these then the sum becomes like a product of all of these individual e to the t times xi values. Okay, yeah. So then we have that So then we have this inequality over here. All right, now this inequality holds for any t, right? Because we just chose an arbitrary t larger than 0. Okay, so we can in fact choose any t larger than 0, and this inequality still holds, even if we pick a t to like minimize this value over here. Okay, because t is a parameter, and possibly for different settings of t, we get different values on the right-hand side. So we can actually pick t to minimize the right-hand side. Okay, and this inequality still holds. Okay. In addition, here now we have that we're looking at an expectation of a product, okay, of a product of a bunch of random variables, right? Each of these things over here is a random variable, right? It's the exponentiation of another random variable, but that's still a random variable. Okay, so now we're looking at the expectation of the product of a bunch of random variables. And now we can use the independence of these random variables, of these individual xi's. Okay, because if we have a bunch of random variables which are independent from each other, then the expectation of their product is equal to the product of their expectations. Okay, so this is only true when these random variables are independent. Okay, but if they are independent, then we get something like the multiplicative version of the linearity of expectations. Okay, we get that the expectation of a product of random variables is equal to the product of their expectations. So therefore, we can take this term over here, and we can put the expectation, on the inside. Okay, we can bring the expectation on the inside, and now we get this expression over here. Okay, so now this is going to be much, much easier to analyze, okay, because now we just need to analyze not the expectation of a product, which is very complicated, right, but we're just going to do these individual expectations of these individual variables, and then we're going to multiply them together. Okay, so then let's do that for the next step. Okay, so now we're going to use this assumption that, we're going to use this assumption that the xi's are independent Bernoulli variables. Okay, so they're either going to be 0 or 1. All right, and if so then the expectation of each of these individual terms. So now we're going to look at these individual terms. The expectation here is it's going to be 0 with probability 1 minus p, right? So if you put a 0 here, then you just get that it's going to be e to the 0th, okay? And it's going to be 1, right? So if you put a 1 over here, right, then it's going to have this probability of this value, okay? So the expectation is just the sum of these, and then so we get that this is the expectation, and then by using the formula for exponentiation, we can get that this is going to be at most this expression over here, okay? Yeah. Okay, so then now we wanted to get the expected value of t times x, where x is the sum of all of these individual xi's, right? But here, if we assume that all these xi's are equal to each other, and then we have n of these, right? Then this expectation over here is just equal to this expectation to the nth power, right? Because we said that the yeah, so then we're gonna start over here. All right, so we're gonna start over here, right? So we want the expectation of e to the tx, right? And then we saw that what we can do is you can actually bring the expectation inside the product, okay? And each of these individual terms we said is equal to this thing over here, right? So therefore, when you multiply n of these things together, you just get this expression over here. Okay, all right, so now we have that, so now we have this inequality over here, and now let's take a delta larger than 0, and define t to be the log of 1 plus delta, okay, and then a to be 1 plus delta times n times p. Okay, so notice that n times p here is the expected value of capital X, okay, because x is the sum of n of these variables, and then each one of them has expected value p. So x has expected value n times p. Okay, so a here is basically 1 plus delta times the expected value of x. All right, so now we have that e to the tx is going to be at most, let's see, delta times mp. Okay, right. So then if you do e to the t power, okay, e to the tth power is just going to be 1 plus delta, right? Because t here is log of 1 plus delta, right? And then you subtract, so e to the t minus 1 is equal to 1 plus delta minus 1, right? So that's equal to delta here. And so therefore you get from here that you get, this is at most e to the delta times mp, okay? And also e to the negative ta, well, a here is just this thing over here, right? And then t is well, e to the negative t. Okay, e to the negative t is going to be t is going to be 1 divided by 1 plus delta. Okay, and so e to the negative ta is just this thing, right, to the 8th power, which is this thing over here, Right. So yeah. So now we are. Let's see. Yeah. So now we're done. Okay. So now what we're saying is that the probability that x is at least this, okay, is going to be at most this probability. Right. So this is the right. Okay. Yeah. So that gives us the final bound. Okay. So now so that's the proof of one of the basic versions of the Chernoff bound. So now let's actually use this. Give some examples of how we can use it to analyze certain randomized algorithms. Okay, so the first one is we're going to use the Chernoff bound to analyze this coin flipping problem that we've been talking about several times, right? So so now we're going to flip a coin n times, okay? And we're going to look at the number of heads that we get in n flips, okay? And we expect to get n divided by 2 heads, okay? So now we're going to look at the probability that we actually deviate from the expectation. So what's the probability you get at least n over 2 plus delta heads, okay? Or sorry, plus lambda heads for some lambda. Okay, so so now the coin flips are all independent. So therefore we can apply the Chernoff bound. Okay, so in fact we're going to use the first part of theorem 1. Okay, so so let's just go back to theorem 1 over here. Right, so theorem 1 is saying you have a bunch of random independent variables, right? What's the chance that their sum is more than 1 plus delta times the expectation? Okay, and this is going to be at most e to the negative mu times delta squared divided by 3. So we need to figure out what this delta term over here is. Okay, so yeah, so we're going to rewrite this. So the probability that x is at least mu plus lambda is going to be the same thing as the probability x is at least mu times 1 plus lambda divided by mu. Okay, so now this here is going to be our 1 plus delta term. Okay, so sorry, in fact, to make this easier, this the delta is equal to lambda divided by mu. Okay, and by the first part of theorem 1, we have that this probability is going to be at most negative delta squared divided by 3 times mu. Okay, so if you simplify that, you're going to get that this is going to be equal to e to the negative lambda squared divided by 3 mu. Okay, so now mu is yeah, so mu is n over 2. Okay, so now let's try different values of lambda and see what these probabilities are. Okay, so first let's try lambda equal to square root of n. Okay, so in that case, lambda squared is order of n. Okay, so so if you plug order of n into this equation over here, right, and then we have that mu is equal to n over 2. So then what you get is that so you have e to the negative, you have order n, right, divided by n over 2. And so this is going to be something like e to the negative, these things are going to cancel, the n's are going to cancel. So this is some sort of constant over here. So we're going to get that this is e to the negative some constant. Okay, in other words, this probability here is going to be some constant. So this is saying that if you flip the coin n times, the probability that you get more than, let's say, square root n more than your expected n over 2 heads. Okay, that probability is at most constant. Okay, so for example, you have maybe like a, let's say a 10% chance of getting more than square root n heads, more than your expectation. Okay, of getting at least square root n more heads than you expect to. Okay, so now, next let's try a larger value for lambda. Okay, so we expect that the bigger we make lambda, right, the smaller the probability that we get more than mu plus lambda heads. Okay, so let's make lambda a bit larger than square root n. Let's now make it square root of n times log n. Okay, so in that case, we're still going to use this. We're still going to use this bound over here. So we have e to the negative lambda squared divided by 3 mu, right? So if lambda is equal to this, then lambda squared is just, it's going to be n log n, right? And then we're going to divide this by 3 mu, right? So mu here is equal to n over 2. Okay, so we're going to divide by 3 times n over 2 over here, right? So the n's are going to cancel, and basically we're going to be left with a term which is something in the order of log n. Okay, actually it's going to be negative log n because you know, we need this negative over here. So therefore, the probability that x is more than mu plus lambda for this larger lambda here, right? This is going to be at most e to the negative order of log n. Okay, so we don't really know what constant, what's the constant over here, so let's just call this a c. Okay, so in the big O, there's some sort of constant c, and so this is equal to e to the negative c times log n. Okay, so which is equal to 1 divided by n to the cth power. Okay, for some constant c. Okay, so now let's just think about what this means. Okay, so this means that as n gets larger, right, then this term here is going to get smaller. Okay, meaning that as you flip more and more coins, right, the probability that you're going to be more than n log n away, root n log n away from your expectation. Okay, this is going to decrease polynomially fast. Right, so whatever c is, whatever c is over here, if let's say c is 2, okay? So this means that you know, you're going to decrease at a rate of 1 over n squared probability that you have this lambda deviation from your mean. So in fact, these types of probabilities come up quite often, okay? So this sort of decreasing at a polynomial rate, right? So in fact, we're going to call this situation, we're going to say an event occurs with high probability. Okay, we're also going to abbreviate this WHP. Okay, so it occurs with high probability if the probability of the event is at least 1 minus n to the c. Okay, for some, n to the negative c. Okay, for some c larger than 1. Okay, meaning that, yeah, sorry about this. There should be a negative over here. Yeah. So meaning that meaning that, you know, as you make n larger, okay, the probability of this event happening gets very, very close to 1. Okay, because this n to the negative c, right, this is going to you know, approach 0 as you make n larger. Okay. Yeah. So then this is what it means to for that to have happen. And so you know, just to use this, so we're saying that x is going to be at have at most n over 2 plus order of, you know, root n log n heads with high probability. Okay, because the probability you get more than that number of heads, more than that deviation from your expectation is going to be just 1 divided by n to the c. Okay, so yeah, so with high probability you get at most this. Okay. Oh, right, and then you can actually illustrate this pictorially. So what this means is, so this picture here is showing the probability of getting various numbers of heads when you flip n times. Okay, so the highest probability is to get exactly n over 2 heads. Okay, and as you go away from n over 2, then the probability you get that number of heads is going to decrease exponentially. So in fact, if you look at the total probability that you get, so if you look at this region of with root n log n around n over 2. Okay, so we're going to look by that much in both directions of n over 2, right? If you look beyond those two regions, the probability you get less than this amount or more than that amount of heads is really small. Okay, so if you add up these two green areas, those two things are at most have 1 over n probability of occurring. Okay, so very likely you're going to be somewhere in this region, meaning that you get exactly n over 2 heads plus some sort of deviation from this, okay, which is on the order of n log n, root n log n. Okay, so that's just one illustration of the Chernoff bounds. So next, we're actually going to use the turn-off bound to in an algorithmic way. All right, so we're going to use it to do this problem of load balancing. Okay, so let's assume a very simple model for load balancing. So here, suppose you have n computers, okay? And then the computers are processing these jobs that are being given to them. And you basically want the computers to process the same number of jobs so that they all have about the same amount of work to do. Okay, so this way you can actually complete all the jobs as quickly as possible. Okay, so specifically you have n computers, and then we're going to get, so these jobs are going to come, are going to be arriving at these computers. Okay, and we have to decide which computer is going to do which job. And furthermore, let's assume the jobs have equal sizes. Okay, so we're making lots of assumptions here, right? Yeah, the computers have equal speeds, the jobs have equal sizes, any computer can do any job, right? There's no ordering constraints among the jobs. So we're making lots of simplifying assumptions, but still, you know, for certain workloads, this is reasonable, right? So for example, if you're doing a web server, right, this is kind of a reasonable model for the web server because, you know, for the web server, you might have several server computers, right? And then you're getting these web requests to, you know, to access some web page. Okay, so these requests are usually about the same size, right? Usually you have to do about the same work to access any web page, and then any processor, any computer can process any request. Okay, and these requests are independent from each other, so you can do them. Usually you can do them in any order. Okay, so this is a somewhat reasonable model for load balancing. Okay. And again, our goal is to assign each of these jobs. So as they arrive, we have to give each job to some computer. Okay, and our goal, again, is to make all of the computers process about the same number of jobs. Okay, so, so that way we finish all the jobs as quickly as possible. Okay, and so this is called load balancing, right? Because we want to balance all the computers. Okay, so there are many different ways to achieve this load balancing. So one way is just to assign the jobs round robin order. Okay, so so we can, you know, the first job you give to the first computer, right? Second job you give to the second computer. Right? So then you go like 1, 2, 3, 4, and then eventually when you get to the last computer, right? So if you have like 4 computers, you give the jobs to computers 1, 2, 3, 4, right? And then you wrap around and then give the 5th job to the first computer. Okay? So you always assign these jobs like 1, 2, 3, 4, 1, 2, 3, 4, and so on. So that's round robin. And because these jobs have equal sizes, then this round robin actually achieves almost perfect load balancing. Okay, so as perfect as possible, right? Because at most two processes differ in the size of one job. Okay. Yeah. However, the problem with round robin is that you have to keep track of like which computer is the next one to get the job. Okay, and presumably, well, I mean, one way you can do this is with a centralized controller. Okay, but then the centralized controller becomes a bottleneck because every time you get a job, you have to go ask the central controller like who's the next computer to get a job. Okay, so you have a lot of communication going to that centralized controller. So this might not be such a good approach if you're getting jobs very, very fast, right? If you're getting like, you know, thousands of jobs a second, then you might actually overwhelm this centralized controller. Okay, so instead we can do something random. Okay, so we're going to use randomized load balancing, and the algorithm, if you want to call it that, because it's so simple, all we're going to do is every time we get a job, we're just going to assign it to a random computer. Okay, so that's the entire algorithm. Okay, each time you get a job, you just pick a random one of your n computers and do it, and have that computer do it. Okay, so now the question is, how good is this algorithm, right? How well does this achieve load balancing? Okay, so to analyze that, we're going to compare the number of jobs that we get to the number of computers. So suppose that at some point we've received m jobs. Okay, so then in expectation, we expect every computer to get m divided by n jobs, right? We have n computers, each of these m jobs goes to a random computer. So then in expectation, you expect each computer to get m divided by n jobs. So the question is how much is the actual load of each computer going to deviate from the expectation? And to analyze this, we're going to use the Chernoff bound. Okay, so to do this, let's let x of I be the actual number of jobs that the ith computer gets. Okay, and then we want to find what is the most loaded computer. Right? Ideally we want everybody to get exactly m divided by n jobs, but in practice, some computer might get more jobs. So we want to know which computer gets the most jobs. Okay, so then we're going to let capital X be the maximum of all of these xi values. Okay, and then we want to make sure that these xi values and this maximum xi value, we want to make sure that both of them are not too much larger than the expectation. Okay, so if both these values are close to the expectation, then we know that the load is balanced between these computers. Okay, so to do this, we're going to define another random variable here, yij. Okay, so yij is going to be saying that let's look at the jth job. Okay, and if that is assigned to the ith computer, if the jth job is assigned to the ith computer, then yij is 1, and otherwise it's 0. Okay, so basically yij is keeping track of which job is being assigned to which computer. Okay, so first of all, the probability that yij is 1, right, is equal to 1/nth. Okay, because if you pick a random, if you pick a computer and a job, okay, right, then there's a 1/n chance that this job was assigned to that computer, right? Because the jth job was assigned to a random computer, so the probability that it's assigned to a specific computer number I, that's going to be 1/n. Okay. Also, if you look at the total number of jobs that were assigned to the ith computer, okay, well, that's just equal to the sum over j of all of these yij values. Okay, because these yij values are saying, like, is the first job assigned to the ith computer, right? Like yi1 is whether the first job is assigned to the ith computer. Okay, because if it was, then you put a 1 there, and otherwise you put a 0. Okay, and then yi2 is the second job assigned to the first the ith computer, right, and so on. So if you add up yij over all of the j's, then you get the sum over whether any of these jobs were assigned to the ith computer, right? So you get the total number of jobs that were assigned to the ith computer. Okay, so now notice that this xi, right? So this is the sum over a bunch of yij values. And each of these yij values is independent from each other, right? Because whether the jth job is assigned to the ith computer is independent from whether like the j plus first job is assigned to the ith computer, right? Because we do all of these assignments randomly each time. So therefore, all of the yij variables are independent from each other, and xi is the sum of a bunch of these independent random variables, right? So now we can apply the Chernoff bound. So in fact, anytime you see that you have a random variable which is the sum of a bunch of other ones, and those other variables are independent, right, then you should think about whether you can apply the Chernoff bound. Okay, so let's do the do the bound. All right, so we're going to consider several cases depending on the number of jobs that we have. Okay, so the first case is where so we have we have n computers. Okay, so the first case is that we also have n jobs. Okay, so so we only have a few jobs, right? So in that case, since you have the same number of jobs as computers, right, then you expect that each computer is going to get 1 job. Okay, so therefore the expected value of xi, right, is going to be 1. Okay. And this is so we're trying to bound the probability that xi is very large. Okay, so we have that the expected value of xi, the expected number of jobs that the ith computer gets, is 1 for every I. Okay, so now we're going to look at the probability that this x here. Okay, so remember that x is the largest of these xi values. Okay, so we're going to look at the probability that the most heavily loaded computer, okay, has a certain number of jobs. Okay, in particular, we're going to look at this value. Okay, what's the probability that the most heavily loaded computer has more than log n divided by log n jobs? And we're going to show that this probability here is small. Okay, it's going to be at most 1 divided by n. And if we can show this, then what that means is that with high probability, okay, meaning that with probability at least 1 minus 1 over n, right, every computer is going to get at most log n divided by log n times its expected number of jobs. Okay, so that's what this statement here implies, right? Because this is saying that you expect to get 1 job each. Okay, and if the most loaded computer, okay, this capital X here has more than log n divided by log n jobs, if that probability is very small, okay, if that's only at most of 1 over n probability, then with at least 1 minus 1 over n probability, every computer gets no more than this number times its expected number of jobs. Okay, so all right, so to analyze this probability that this about this big X, right, we're going to focus on the individual xi's first. Okay, so let's just pick any I, right, and then let's set delta to be this value, okay, to be this log n divided by log n. Okay, so then we can now use part 2 of theorem 1. Okay, so this delta here is going to be a value larger than 1. So if you use part 2 of theorem 1, so we're going to have to go back quite a bit. Okay, so part 2 here was applies when delta is larger than 1. Okay, and it's saying that this thing here is going to be at most e to the negative mean times delta log delta divided by 3. Okay, so we just have to plug this delta log delta divided by 3 times the mean into this formula. So let's do that. Okay, yeah, so the mean is going to be 1, right? And then here you have delta log delta divided by 3. And then because your delta here is log n, okay? So then if you do delta times log delta, right? So log delta is equal to basically order of, so it's going to be log n, right? Yeah, oops. Right, minus triple log n, okay, right? Log n, okay, right? So we can just ignore this term and say that this is order of log n. So therefore, delta times log delta equals this order log n, oops, right? Okay, times this delta here is going to be log n divided by log n, right? Okay, so then these things are going to cancel, and so you get that delta times log delta equals order log n. Okay, and then yeah, and then so we have this expression over here, right? And then by choosing the right constant, we can get that this is going to be at most 1 divided by n squared. Okay, so we have that the probability that any individual computer has more than this number of times, has more than 1 plus delta times its expectation is going to be at most 1 divided by n squared. Okay, and this holds for every I, right, for every computer. Okay, so now the probability that, what about the probability that any computer has has this condition? Okay, we know that for each individual computer, the probability of this condition is at most 1 over n squared. And now the probability that any of these n different computers, because we have n computers in total, has this condition is going to be at most n times this probability. Okay, so this is called the union bound. Right, so we used this previously, and basically the union bound says that if you look at the event, the probability of like A or B happening, okay, that's going to be at most the probability of A plus the probability of B. Okay, and this doesn't even require any like independence or any other relationships between A and B, right? This is always going to be true. Okay, so each of these individual events is true with at most 1 over n squared probability. So the probability that any of these n different events is true is going to be at most n times that, which is 1 over n. Okay, so this shows that the probability that, and you know, in order for x, which is the maximum value of these xi's, in order for that to be larger than log n divided by log n, we need that one of these xi values is at least that large. Okay, and this happens with at most 1 over n probability. Okay, so this means that, again, the probability that the most heavily loaded computer has this number, more than that number of jobs, is very small. It occurs with low probability. Okay. All right. However, you see that here the relative imbalance is actually still pretty large. Okay, because you know, you expect each processor only just to have one job. Okay, and here we're saying the probability you have more than log n divided by log n jobs is small. Okay, but this value here is still much larger than 1. Okay, so in relative terms, you could still have a computer which has much more you know, number of jobs than the other computers. Okay, and this is because you know, we only had a few jobs for each computer. In fact, we only had 1 job for each computer. Okay, so what you expect is that as we get more jobs, then this randomized load balancing is going to start working even better. Okay, you expect that you know, in fact, if you get many jobs, then you expect that the relative deviation between these different computers is going to decrease more and more. Okay. So this is very similar to the situation where you know, we have these random coin flips. Okay, so if you only flip the coin a few times, then if you look at a relative deviation, right, what's the chance you get more than 10% heads compared to your expectation, right? 10% more than your expectation. That's pretty large if n is small. But as n gets larger, then the probability you get that deviation gets much smaller, exponentially fast. Okay, so then here we're going to do the same thing. We're going to increase the number of jobs that each computer has. Okay, we're going to see that the probability you get a relative error is going to decrease very fast. Okay, so now how many jobs should we think about? So let's consider now m is not going to be n, it's going to be something like n log n. Okay, so let's be specific. Let's make it 16 times n log n. Okay, so in that case, you expect each of these n computers to get 1/n of those jobs, so that's going to be 16 times log n. Okay, and so now let's look at the probability that you get more than 2 times your expectation. Okay, so so we're gonna now apply theorem 2, and we're gonna use delta equals 1 in theorem 2. Okay, so all right, so let's just flip back to theorem 2 over here just to see theorem 2 here. If you use delta equals 1, right, then you get what's the probability x is more than twice its expected value. Okay, so we're just going to plug 1 in here for this entire formula here, right? So if you do delta equals 1, you get e divided by 4 here. Okay. All right. Oops. Okay, so then you get e divided by 4, right, to the muth power. Okay, so mu here is going to be 16 times log n. Okay. Now, if you do some calculations, you're going to find that e divided by 4 to the 16th power is actually less than 1 divided by e squared. Okay, so you can just compute that. And so, yeah, and then so you can just, so the e and the log n are going to cancel out. So this whole thing is going to come out to 1 over n squared. Okay, so so this means that each individual computer, the probability it's got more than twice its expected load is at most 1 over n squared. And so again, you can use the union bound and you can say, what's the probability that any of these computers have more than twice its expected load? Okay, well, that's just going to be n times this thing over here. So that's going to be 1 over n. Okay, so that means that with high probability, with at least 1 minus 1 over n probability, all of the computers are going to have at most 2 times the expected load. Okay, so that means that no computer is overloaded. Okay, but we also don't want any computer to be underloaded, because if it's underloaded, then it's not doing anything. Okay, so now we want to look at what is the probability that a computer gets very few jobs. Okay, and now we can use part 3 of theorem 1, which was about what's the probability x is much smaller than the expectation. Okay, and if you plug in those values over there, right? So then here we have that delta equals 1/2. Okay, so that was part 3 of theorem 1 was something like, had this term 1 minus delta times mu over here. Okay, so for us, delta is going to be 1/2, and if you plug in that that thing into the formula, you're going to get this expression over here. Okay, so by the way, this is why we chose this particular constant 16 over here. Okay, it's because we need that term to like cancel out with the terms from the Chernoff bound. Okay, so here it does cancel out, and what's going to happen is this is going to end up being something like e to the negative 2 times log n, which is 1 over n squared. Okay, so and that's for an individual computer, the chance it's got less than half the expected load is at most 1 over n squared. So therefore, the probability that any of these computers, any of these n computers, has less than half the expected load, right, is just going to be n times 1 over n squared. So that's going to be at most 1 over n. Okay, so if you put together both of these two statements, you get that with high probability, every computer has at most twice the expected load and at least half the expected load. Okay, so that means that all of these computers are pretty much balanced with high probability. Okay. And we were able to get this because we considered having more jobs. Okay, so in fact, if you make m even larger, then you can make these bounds even closer to each other, right? You can so currently we're saying like, there's a good probability it's got between half and twice the average load. Okay, now if you make m a lot larger, you can even say something like, every computer has between like it's hard to write over here, but it has between like 99%, okay, to 101%, okay, the average load. Okay, so just slightly less or slightly more than the average load. Okay, so the more jobs you have, you can see that if you plug in those values into the Chernoff bounds, you're going to get tighter bounds, and so you're going to get better load balancing. Okay, yeah. So basically, this randomized load balancing algorithm works quite well as long as you have a large number of jobs. Okay, so the final thing we're going to look at is this problem called set balancing. Okay, so then here we're going to talk about a bunch of sets. So let's say you have m sets. Okay, each of these sets is going to be a subset of 1 up to n. Okay, yeah. So now you can represent each set as a m-bit vector. Okay, so you have n possible values here. So for example, if n equals 4. Okay, so you have m sets, each of which is a subset of 1, 2, 3, 4. Okay, so if your set is, for example, 1, 3, and 4, then you can represent it using a bit vector just by setting the first bit to 1, right, and then the third bit and the fourth bit. Okay, so yeah, right. So that's just how we're going to represent a bunch of sets. And now the set balancing problem is that suppose you have a bunch of sets, and you want to divide the sets into 2 groups. Okay, and then you want the sum of the sets in the groups to be roughly equal, right? So you have 2 groups, and then each group has a bunch of sets in it, and then if you add up those sets in both groups, that's roughly equal. Okay, so as an example of this, right? So suppose you have the first set, right? So you have, let's say, four sets over here. Okay, so the first set is going to have elements 1, 3, and 4, right? The next one has like 1, 2, 3, right? And then 3, 4, and then 2, 3. Okay. So what you want to do is divide these 4 sets into 2 groups where the number of elements in each group is about equal. So for example, if you put the first set and the fourth set together, right, and then you also put the second set and third set together, right, then both of these groups have 1 copy of 1, a single copy of 2, right? They've got 2 copies of 3, and then 1 copy of 4. Okay, and that's what you want to, and so this is what we want to do. Okay, we want to break this collection of sets, right? This collection of 4 sets into these 2 groups, so that each of these groups has about the same number of copies of each element. Okay, now in this case, we could actually break them into 2 groups with exactly the same number of elements in each group. Okay. But sometimes we can't make things so exact. Okay, sometimes an exact balancing does not even exist. So in that case, we just want to break things into groups that are as close to balanced as possible. Okay, so in order to sort of measure the balance of a grouping, okay, we're going to define this notation here. So let's say that G and G prime are the 2 groups that we divide into. Okay, then what we want to do is we want to minimize this expression over here. Okay, so this expression is saying that we're going to take all the sets in the first group and add them up. Okay, so just like, you have S1 and S4, you add them up as vectors, right? And then you get this thing 1, 1, 2, 1. Okay? And then you're going to take the other group, G prime, and you're also going to add that up. Okay, so you can also represent that using a vector. And then now we can just compare these 2 vectors and see how close they are. Okay, so we're going to subtract the 2 vectors, and then we're going to take the L infinity norm over here. Okay, so that's what this infinity thing denotes. And remember, the L infinity norm just it's going to take the large. So given a vector, it's going to take the component with the largest value in absolute value. Okay, so for example, the L infinity of this vector 1, 2, negative 3, and 1, right? This is, we're going to take the term with the maximum absolute value, which is going to be 3. Okay, and so this term here, right, the L infinity of the difference of these 2 sums, right, this measures like what is the maximum difference between these 2 sets for any element. Okay, and we want to minimize that amount. So as an example, if you have 4 sets over here, okay, now there's no way to exactly balance these sets. Okay, no matter how you group them, there's no way to get an exact balancing. However, if you put S1 and S3 into one group and then S2, S4 into the other group, right, then the imbalance is, well, if you add up S1, S3 and subtract S2, S4, right, then you get that, you get this vector. So the imbalance is going to be 1. Okay, so oops. Okay, is going to be 1 over here. Okay, and that just basically says that the first group has an extra copy of 3 compared to the second group, right? But it's got the same number of copies of 1, 2, and 4. Okay, so yeah, so we want to so our goal is to find a grouping which minimizes this imbalance. Okay, which minimizes this value over here. Okay, now this is actually an NP hard problem because actually, yeah. So I'm not gonna sort of prove this, but anyways, it's hard to do this. Okay, and if you do a brute force method, you would just have to try all the possible groupings, right? So we have m different sets here, right? So then you would have to try like 2 to the m number of groupings. Okay. So instead, we're going to give a randomized algorithm, which is going to ensure pretty good imbalance. Okay, it's going to ensure that the maximum imbalance is not very large. Okay, so in fact, it's going to ensure that the maximum imbalance is at most, root of 4 times m times log n with high probability, where m is the number of sets that we have, and then n is the number of elements in this universe, right? So n is like, so we have m sets, each of which is a subset of 1 to n. Okay, yeah, and remember that the maximum imbalance is m, right? Because you have m sets, so at most you can have m imbalance. And so, so this is saying that we can actually get a randomized algorithm with imbalance, which is only sort of square root of m, okay, times some of these other factors, which are pretty small. Okay, and so this algorithm is actually very simple. Okay, At the beginning when we talked about randomized algorithms, we said one of the main advantages to randomized algorithms is that sometimes you can get very, very simple algorithms, okay, that still work pretty well. Right? So with the load balancing algorithm, that was very simple, right? You assign to a random processor, and with the set balancing algorithm, okay, that's equally simple. So you're just going to take each set, okay, and assign it to a random group, okay, either the first group or the second group, and you just do that randomly. Okay, so nothing could be easier, but it turns out that even with this very, very simple assignment, you can get a reasonably good bound on the imbalance. Okay, it's basically going to be root m imbalance compared to the maximum possible imbalance, which is m. Right? So yeah. Okay, so the way we're going to analyze this algorithm, okay, so we're going to show that this random assignment is actually pretty good. The way we're going to do that is, suppose, let's consider the ith item. Okay, so we have n items, right, 1 up to n. Okay, so let's just consider the ith item. Okay, and let's say that among all of these sets, so we have m sets, let's say that item I belongs to k of these different sets. Right, it doesn't have to belong to all of the sets. Let's say it just belongs to k of these different sets. Okay, now for the jth set, okay, for the jth set that this item I actually belongs to, right? It belongs to k different sets, and for the jth such set, right? Let's define x of j to be 1 if s. Oh, right. Okay, so yeah, we're focusing on this set S, which contains this item, right? Contains item I. Okay, and if we put S into the first group, we're going to set x of j to be 1. And if we put S into the other group, then we're going to set x of j to be -1. Okay, so then the imbalance for this ith element, okay, is just the sum of all of these xj values, right? Because for this ith element, we just want to look at how many times was it put into the first group versus the second group, right? Each time it's put in the first group, we have a 1 here, and then each time it's in the second group, you have a -1. So if you add those together, right, you get either a positive or negative number, but the absolute value of that number is just equal to the imbalance for the ith item. Okay, so we're going to set b of I to be the imbalance for the ith item, which is equal to the sum of all of these xj's. Okay, so now, because all these sets are assigned randomly, okay, so then for each of these sets that we're considering, right, it's assigned, xj is assigned to the, it's put into the first and second group randomly, so therefore this xj is like a random variable, which is either 1 or -1 with the same probability. Okay, and furthermore, because you assign each set independently from all the other sets, then all of these xi values are independent from each other. Okay, so so this I belongs to k different sets, and each of these sets is either going to be in the first or second group independently from each other. So therefore, all of these xi values, x1 up to xk, are independent from each other, and they have values either 1 or positive or -1. Okay, so now, and then we have that bi is the sum of all of these independent variables. Okay, so now since we have a sum of independent variables, we can apply the Chernoff bound, but we're going to use the version 3 of the Chernoff bound. Okay, because version 3 was let's just go back to version 3 over here. So that was actually specifically designed for these random variables, which are plus and -1. Okay, so you notice that. Yeah, for version 3 here, we are looking at variables which are plus or -1. Okay, and they have equal probability of being either one. Okay, and so what it says is that the probability that the sum of these random variables is more than delta is at most e to the negative delta squared divided by 2n. Okay, so then let's plug that bound into what we have here, right? So we have okay. Oh, so now we have two cases. Okay. So the first case is that this k here is actually small. Okay. So the k in the first case, it's less than √4m times log n. Okay. So in that case, the maximum imbalance, because this item only belongs to k of these sets, okay, and k here is small, then the maximum imbalance obviously cannot be larger than k, okay, because here the imbalance is just the sum of the of k of these numbers, okay. So the maximum imbalance cannot be large, and that's what we wanted to show, right? We wanted to show that for any item, the imbalance on that item is not going to be too large. So if k itself is small, then the imbalance on that item is also going to be small. On the other hand, if k is large, right, then we can actually use the third theorem, the third version of the Chernoff bound, and then there we have that the probability that that this b of I value, the sum is larger than delta, is going to be less than where does this 2 come from? Let's see. So let's see. All right, so I'm not sure where the 2 comes from. Anyways, let's just sort of ignore this 2 term over here. Okay, but yeah. Anyways, okay, but so the main term is going to be this e to the negative what is it? E to the negative delta squared divided by 2n, okay, or 2k rather, okay. So here we're summing over k of these values, so here we're going to have a 2k over here, right? And then the delta value, right? So our delta value here is going to be this thing over here, right? So then we have e to the negative delta squared divided by 2k, right? And then k is, okay, so we get this equality over here, and then k is going to be at most m, right? Because you have only m different sets, and so k is going to be at most m, and so you have this thing over here, right? And then you do some simplifying, and then you get that the probability that the ith item has this much, has at least that much imbalance, okay? That's going to be small. That's at most 1 over n squared, okay? And so now we can apply the union bound, and we can look at what is the probability that any item has large load imbalance, okay, or has large imbalance, okay? And this is going to be just n times this probability, okay? So therefore, the probability that any item's imbalance is larger than this value is going to be at most 1 divided by n. And so if you combine this with the first case, right, where you know, k simply is a small value, then this shows that, you know, with high probability, no item has imbalance which exceeds 4m times log n, okay, square root of 4m times log n. Okay, so yeah, so that's the end of this. Yeah, so the next time we're going to look at some more randomized algorithms in a distributed computing setting. Okay, so then see you guys next time.